you may notice I changed the title a little even from what you had in the Zoom link. We're going to talk about zero-inflated outcomes, correlated random effects, but I may not be able to show you lots of empirical results. Let's just give the main message in the beginning. I think I learned not to leave everything to the end of. If you have to leave early, I want to give you the story first. So we are going to deal with clustered data of some form. These like a familial data, longitudinal data. These data afford us more methods or tools for causal inference using observational data. But we do need to make sure we understand what our target parameters are. And more importantly, we need to know if the statistical estimator that we're using are estimating the target effects of interest. And in fact, many statistical models estimator exist, and some operate under different assumptions. I think we need to change the paradigm from trying to decide which model is the best fit or provide the best prediction to being able to support decision-making in a rigorous way. Even when the assumptions are untestable, we can still get some clues with careful analysis. And I will use some simulations to make these 2 points that are beautifully articulated by Andrew Gelman and Xiaoli Meng. One is, because of the existence of the multiple competing approaches for inference and decision making, we can know for sure there's no single method dominates the other. Secondly, the world is complex, the data are messy, and our theoretical framework may not be able to capture all of the intricacies of these data. We may not be able to understand all the biases and inconsistencies, but through critical thinking, we can still make useful inference, scientifically useful inference. This is mostly because he calls this so-called low resolution space for action decision making. No matter how complex your model is, sometimes in the end, your policymakers just want to know to act or not to act. So there may be, because of this low resolution, we may have lots of flexibilities in accepting the quantitatively different results caused by different problems in the data and assumptions and so on, but not to despair, we can still do some good work, right? So I'm going to use some simulation to support these points. The simulation will show you that sometimes when your target parameter, for example, is the marginal effect, or what we call the average treatment effect, or average treatment effect on the treated, all these other parameters, coefficients you get from an outcome model, coefficients you get from treatment model for estimating the propensity scores, or whether the model has correlated random slopes or not, whether you use a marginal model or not, we can consider them all nuisance parameters. In the end, you want to find reasonable estimate for the effect of interest. And in my simulation, I actually found some of these average treatment effect on the treated is sensitive to the proportion of people who are treated in your study. And of course, multiple statistical methods can lead to same action recommendations, right? So the real story behind all of this is we had an evaluation project for a state-sponsored home visiting program for pregnant women. And as a consulting statistician, I was funded on the project for like 3% of my time. And then we found out the evaluation actually turned out to be quite complicated. There's some features of this evaluation makes the analysis hard. First of all, we have 3 intervention groups, These are not randomly assigned. People can choose whichever they want to do. Secondly, this intervention group of interest, which is this sponsored home visiting program, the proportion of women in that group is very, very small compared to the other two intervention groups, two groups. And thirdly, this evaluation goes over a 6-year period. So some outcomes are longitudinal for some of the participants, but in a very selective way, because this is going to depend on who have more than one pregnancy during the study period, right? And finally, the primary endpoint is the count data, is the number of emergency room visits during pregnancy, and it's zero-inflated. And it has this so-called endogenously determined period of time, because during pregnancy, this pregnancy time is influenced by other things as well. Preterm babies, if you have preterm baby, you have a shorter time period to study. Right? All of these complications made us, well, so then I'll show you the data, I guess. So this is how just a simple histogram of the outcome. The ED visits during pregnancy by the 3 groups, the Medicaid women only. There are more than 60% women in this group. And there's a maternal infant health program in Michigan for Medicaid women. It's about 30%, over 30% of the women in this group. And this intervention of interest, which adds on top of the MHP, we add this sponsored home visiting program. And the number of participants in this group is 1% of the total population, like if we count all of the births in the state, right? So when we consider all these features, we naturally set out to think, oh, we need a model that can handle all of these complexities. We need a zero-inflated model. We need correlated random effects to deal with endogeneity. And we need also consider the correlation over time if you have multiple observations. So probably not surprisingly that in the end, our initial ideas did not work out so well. There are several reasons related to these features of the study, this data set, right? So we created this thing, we tried to estimate this using simulated maximum likelihood and so on. But since it didn't work out so well, we went back to the basics and asked ourselves that what is, we know that we want to estimate this effect if we roll out this home visiting program to the entire state, right? If we apply this to the other groups, what would happen? That's one question. Another question is for the women in the treatment group in this home visiting group program itself, had they not participated in the program, what would have happened? So the first question is the average treatment effect. The second question is the average treatment effect on the treated. So these are the effects of interest. Then do we really need that complex model to achieve this goal? Like the complex model, we are estimating conditional on the random effects, conditional on the observed covariates and so on and so forth, gives us a conditional effect, but that doesn't really give us the flexibility to answer these questions. We can, if we get empirical posterior prediction out of that and do the averaging and so on, but is that complexity worth doing or not? That's the second question. So it turns out in econometric literature for correlated random effects, and in the literature or application of the sibling comparison design in epidemiology, lots of inroads have been made recently, strategies be proposed that can help us. For example, in this sibling comparison study design, we can draw a typical causal diagram like the picture here. You have a family with 2 children, and we have a child-specific exposure. We call it X, and Xij. I index the family, J index the child, and we have outcome Yij, and observed measured confounding variables summarized by Cij. Could be the Cij could be child specific, like the air pollution during pregnancy for each child, or it could be family specific or shared confounding by both children, like mother's education and measured family income and so on. This had been of interest to many epidemiologists, and the causal effect that had been reported mostly are the conditional effects, but the causal effect of interest could also be the so-called average treatment effect or average treatment effect on the treated. If we use a little bit of a notation math to describe these parameters, we use an uppercase superscript to represent the counterfactual intervention, like y x equals 1 means the potential outcome for the person if the exposure is set at the value of 1, and y superscript x equals 0 is the potential outcome for the individual if the treatment is set at the value of 0, and we are interested in the population effect marginally, so we use expectation to find the average treatment effect. And the average treatment effect on the treated simply look at the subpopulation who actually had been treated and ask the same question, what would have happened had they not been treated? That's corresponding to the 2 questions that we were talking about earlier for the home visiting program. And a typical fixed effect model that we use to handle this kind of a sibling comparison design is to estimate a generalized linear mixed model, or not a generalized linear mixed model per se, because we want to have a fixed effects here. So the idea is we have this unobserved variable u, and we know that is a confounding factor. It would influence x, also influence y. So in my regression of interest here, we have the outcome y depending on the exposure, confounding variable c, as well as this unobservable u. However, we cannot really do a generalized linear model because in those random effect models, this unobservable u is assumed to be uncorrelated, at least uncorrelated with the exposure of interest. But with this causal diagram, we know that assumption is violated. At least we assume that assumption is violated, right? So but we still want to have consistent estimate of beta 1, the coefficient. And this can be interpreted as the conditional effect of the treatment given C and U. Sorry, this typo, it should be UI. However, there are some limitations to this traditional fixed effects approach. Number one is, if you want to estimate average treatment effect or ATT, you need to find a way to find a valid estimate of U and then marginalize over it and over other covariates to get to the average treatment effect. And in econometrics literature, the estimated U had been proposed long ago for the linear fixed effects model. And recently, Arvid, I don't know how you spell it, so pronounce the name, Sjoland, I don't know. Recently, he extended the approach to log linear fixed effect models to find the predicted U hat and then get the marginal counterfactual. But he also noted that you cannot do this for logistic regression. And number two limitation, which is also related to the limitation of a causal diagram. You know that causal diagram can show causal relationship, but it cannot demonstrate or indicate effect modification. So if there is effect modification by the unobserved confounding, model would change to this second equation, where you will have an interaction between your exposure of interest and the unobservable. Right? Again, this UI is supposed to be correlated with Xij, but it's unobserved. And so we can show that under some conditions, if you do the usual fixed effect estimator, as if you have a model 1 here, you will actually get a bias estimate for this coefficient right here, right? That's the second limitation of the usual approach. And a more subtle kind of implicit assumption of these models that we're using, perhaps, at least for some of them, is the number of children is considered fixed. It's considered conditional on these number of children, what happens. In other words, we are not studying the selection process for who get pregnant. Basically, we're ignoring that process. There might be some consequence of ignoring that process. This, to my knowledge, had not been investigated thoroughly. For example, we recently acquired this Michigan-linked birth certificates data from 1995 to 2019. If we use do a scatter plot of all the babies born using this data, they would show in this gray, all these gray dots, gray circles would be the actual data that we have in the linked data set. However, we would be missing some of these other babies who were born before 1995 to the same group of women, and the babies who were born after 2019 to the same group of women, right? So when we use this, simply use the linked data, ignoring this selection, we are probably committing some sins here, like making assumption about the selection. Who has more than one baby in your data set to be a random factor, which may not be correct. So if we want to really capture the more than 20 years of reproductive history for a woman, or capture almost all of the babies, we can probably only look at a very, very few cohort of women, those who were born between, say, 1974 and 1980 something, right? But again, when we do fixed effects or sibling comparison studies, we typically ignore this, right? So what to do? There's the complication of the outcome. There's the complication of the structure, like the sibling comparison structure, and we have different target parameters. So can we get to those target parameters without sacrificing the assumption that you have this unobservable? So it turns out it has been known for a while in econ and stat literature that if you have a outcome distribution in the linear exponential family, like the normal, the binomial Bernoulli, and the Poisson, and these kind of outcome. If you use so-called quasi-maximum likelihood estimation with a canonical link function, you can identify the parameter of interest in this equation 1 that we talked about before, which is the one that has the unobserved confounding U without the interaction yet. So in that case, it is convenient because then we can easily get to the average treatment effect on the treated by using these QMLEs, or so-called within estimates under some more flexible, some pretty flexible assumptions. This assumption essentially reduced to the mean exchangeability assumption. And more recently, strategies have been proposed separately by in Econ and Felsted to deal with this model 2, where you have interactions or effect modification by unobserved confounding. And even when you have this sample selection problem for an unbalanced panel, which is beyond the scope of this talk. However, so this might be a way to handle this kind of issue, but we were thinking, given that the zero-inflated Poisson model is not in the linear exponential family, maybe we should check to see if these strategies suggested by these authors will work or not to estimate ATT and ATE. So we do a bunch of simulations. I'll show you some here. We start with the simple, cross-section setting, not with an observed heterogeneity, because we want to see if in a cross-sectional setting, you have a distribution that's not in the linear exponential family, would that work or not? So we simulate an exposure which is normally distributed, another predictor Z for the outcome has gamma distribution, and the treatment A follows Bernoulli distribution with this probate model kind of functional form. And you have two potential outcomes. When A equals to 0, you have a zero-inflated Poisson outcome, where the zero inflation proportion is a constant for now, simple case. It doesn't depend on X or Z or A. And then the mixture part, the Poisson mixture part, has this mean function, which has the X and Z interaction. And the potential outcome for Y1 has a Poisson distribution. And you also have this mean specification here. And the observed data is equals to the Y1 if a person is treated, or the observed A equals to 1, or it equals to Y0 if the observed A equals to 0, the person is not treated. So we considered various scenarios where we use alpha 0 here to control for the proportion of patients who are treated. And we use this gamma to control for the degree of zero inflation. And so even if we have this zero inflated model, we want to test these conjectures that we can still use Poisson model, a flexible specification with Poisson flexibly specified mean model with Poisson distribution, and to estimate the marginal effect. So we do two things. One is this Poisson model with the mean of the intervention, X and Z, and A, X and Z, and all the interactions. This is basically correctly, it's consistent in the sense with all the combinations of the covariate patterns that we have in the data generating process. And then we do a second estimator, which is this inverse probability weighted model, where you estimate the probability of being treated, and we use the correct treatment model, probate model for the A, which has this X and Z and XZ interaction. And we try to find the average bias for the average treatment effect or the average treatment effect treated. So here are the simple results here. You have the color indicate the degrees of zero inflation. The gray ones has 10%, green one has 20%, and red one has 30% zero inflation class. And the panel, each of these pictures shows the proportion of patients treated. The first figure here shows, even though we're using a wrong distribution, Poisson distribution, the estimates for the average treatment effect has very little bias. Instead, the IPW can be biased when the proportion of the treated is very small. And you may ask, like, this is it realistic to have such a small proportion of people who are treated? It turns out in our example, it's even less than this 2%. So the IPW can be very inefficient, and when the treatment proportion patient is small, it's actually biased. But when you look at the average treatment effect on the treated, both of these methods seem to give reasonable answer. And even the IPW is still a little less efficient than the outcome model, right? So, so another message, I guess, in addition to show the bias of these estimates, I want to show the true treatment effect. So this horizontal line now indicate the true ATE in different scenarios. So you can see that this ATE increases as the proportion of zero inflation class increase, but it's not influenced by the proportion of treated. So even though the picture is not showing these red lines at the same level, you can look at the value here, they are actually very close to each other, almost the same. So the ATE itself is not influenced by the proportion of treated. However, the ATT is. The ATT also increases as the proportion of zero inflation class increases, but also the ATE actually decreases as the proportion of treated population increases. That is something that I didn't expect, right? So after this simple simulation, without even the longitudinal case, I had this, maybe we really don't need such a complex model. Maybe we should just do the Poisson model. There are fixed effect Poisson model that can deal with unobserved confounding as well. So then maybe we should try do that. But then I remember this setting here is cross-sectional. So what if we have longitudinal data and really have this complicated effect modification by the unobservables? So we do some more simulation in the longitudinal setting. We simulate binary and count data for 2,000 families with varying number of children in each family. And they have this shared unmeasured confounding at the family level, follows the normal distribution. And this exposure is a function of the U, and outcome Y is a function both X and U, and with the interaction between X and U, as we talked about before. And the link function would depend on whether we're looking at the binary outcome or looking at a count outcome. So that's the key data generating process. And we are still interested in this target parameter, which is the Yx equals 1 minus the potential outcome Yx equals 0. Even though X is a continuous variable, we can think of this as one unit increase. What is the average effect of that? Right. So we consider six different statistical models, estimators. And the first three are the ones that we typically see in empirical research. One is this linear probability model with a fixed effect estimator. The advantage is that U is allowed to be correlated with X in this model, and you can estimate the beta 1 consistently if this fits the data generating process. Second is this fixed effect logistic regression, or so-called conditional logistic regression model, which also allows this UI to be correlated with Xi, same thing as the fixed effect Poisson model. These are estimated by conditional CMLE, the spelling here CMLE, conditional on some sufficient statistic. And the usual between within model with this cluster mean Xi in place, replacing this unobserved UI. We model the so-called between within model under the assumption that Xi bar can be used as a proxy for the unobservable, right? That's the usual models. And now we can augment this usual BW model with some cluster variance as well. In addition to the mean X bar, you can put X double bar, which is the within cluster variance, and even more complicated, suggested by Yolander using the splines for the cluster mean and the cluster variance, and allow interactions between the exposure and the splines. And finally, I use this Mundlak Mundlak-like model to name this, but this is also just a between within model, except it has more flexible specification for the effect of the UI on different J's when you have this interaction between the families with, say, 2 children versus a family with 3 children. They can have different effects. These are the models that we estimate. From all of these models, we try to calculate bias for marginal effects and bias for conditional effects, because some of these coefficient, some of the method does not give you marginal effect easily, so we compare the estimate with the true conditional effects. For example, this binary case, when you have the conditional logistic regression, the coefficient is the log odds ratio, and we know the true log odds ratio. We calculate the bias by for the conditional odds ratio. But for the others, similarly for the between within coefficients in these in model 6 here, which is like equation 6, model 3 here, and model 4 and equation 7, there's one coefficient. Maybe you can interpret that as the effect of interest, and we compare that with the true effect, true conditional effect. And then for the rest, we calculate the marginal prediction, the estimated as average treatment effect, and compare that with the true effect to calculate the bias. So this first figure shows the binary case and the horizontal, the bias for all these methods. You can see that the first thing that jumps at us probably is that the coefficients for the conditional logistic regression and the usual between within model and augmented between within model, these coefficients are biased for the conditional parameter of interest. And then what about the marginal, which is the average treatment effect, right? We can use the between within and augmented between within and the between within spline and Mundlak to calculate marginal prediction. You can see they perform really pretty well. And interestingly, the linear fixed effects model here actually worked pretty well. This linear fixed effects here, even though it didn't consider interaction, this bias is not very big. And then second, for the count outcome, we simulate the Poisson distribution first. And you can see now the linear fixed effects do not work so well. You will have bias for the ATE. But the coefficient for the fixed effect Poisson and the usual BW between within plus variance models are now again biased for the conditional log risk ratio, rate ratio. But the marginal prediction for the usual BW model and the BW with variance model actually worked better than the marginal prediction you get, marginal effect estimated you get from the BW spline model and the Mundlak estimator. There's a much bigger variation in the BW spline model than other cases, which is suggesting when you don't need such complexity, probably we shouldn't include them. Then we do this zero-inflated case, and we have zero inflation class, CIJ, sorry for the notation. This C means zero inflation class, as a function of X and U. And the mixture is the underlying Poisson distribution that depends on X and U again. And if you are in the zero inflation class, you always have outcome equal 0. And if you are not in that class, you have a Poisson distribution. This is the zero inflated Poisson distribution in a longitudinal case. Right? And we consider different degrees of effect modification, which is this beta 2 parameter here. And here's the results. When you do a linear fixed effects model, again, this compared to the average treatment effect, you get pretty good, decent estimate, actually. But that summary there, sorry about that summary there is a little bit wrong here. The linear fixed effects model are generally unbiased or has very small bias. But the fixed effect Poisson model, where you only allow the unobserved confounding without interaction, would give you very biased estimator of the beta 1. Beta 1 is interpreted as the effect of interest of X on the outcome, conditional on these parts, right? So you will have biased estimate. And similarly for the between within and between within plus variance coefficients, those are also biased. But again, we calculate the marginal estimate average treatment effect, and you can see the usual between within and between within plus the variance estimate actually are not so bad. And with spline and the Mundlak, sometimes they perform well, but sometimes because there's so much variation, you don't get actually cannot show that this one has very big bias here. So what is the story? Like I guess all these simulation basically is telling us that no method dominates the others, right? I hope this shows that yes, no method would dominate others. Also, different methods might get to the same effect that you are interested in, right? So now what are we gonna do? So our conjecture that we might need this complex model, what should we do based on the simulations that we have done? The idea is, can we use this simulated maximum likelihood method to estimate some coefficient of interest from this complex fixed effect zero inflated Poisson model that we originally proposed? Or do we really need to do that? Because remember, the action space, again, is just a yes or no. Maybe we don't really need that much of a complexity in our estimation. The estimation for the simulated maximum likelihood have this idea that even though the U is unobserved, I can make some assumptions about the distribution of U and approximate by averaging the density here, and then get to this likelihood function for the observed data. But this method is going to work if you have correctly specified the distribution for U. If this U distribution is wrong, you will get pretty big bias from this method. So how is this useful then? Should we do the simulated maximum likelihood zero inflated Poisson model at all, or should we not? If we can get the different distribution of U and get to the same estimate sign of the estimation of the coefficient of interest, maybe that's useful because it tells us the direction of the treatment. But there's a huge limitation because we cannot estimate the marginal effects, which you typically need for, say, doing cost-effective, cost-benefit analysis, right? So this leads me to this final, I guess, thoughts for this complex state-sponsored home visiting program evaluation again. I would say now we learned from these simulations and the structure of the data and considering the target parameter of interest, maybe we should follow these analytic steps. First, we use this BW or Mundlak approach with flexible specification, but not too flexible, maybe too much for asking too much of your data. Sometimes it's troublesome, right? And use log-link function. We can perform some Hausman type test to check for endogeneity and effect modification. If the effect modification and endogeneity are rejected, then we can proceed to deal with the inflation problem using zero-inflated Poisson or zero-inflated negative binomial, and test for inflation. And if zero inflation is rejected, then we can reduce this even further to gain more efficiency to go to the random effect Poisson model with the cluster robust standard errors for inference of the coefficient of interest. If it's not rejected, we'll just stay with A and add the cluster robust standard error for inference. And if the endogeneity and effect modification cannot be rejected, we either can use this BW method to get to some marginal, or actually using one more method to confirm this is true or not, which is the step 2, which uses this fixed effects Poisson model for the direction of the effect of interest. If this direction is consistent with what we found in the BW approach, we can actually proceed with the BW, because that allows us to generate the ATE and ATT and make cluster bootstrapping for inference, for the marginal effect. But if it's not consistent with the BW models, we probably have to resort to this complex modeling assumptions and check for directions. And I'm obligated to talk about this other approach. If all of these fails, we have this more complex models, this copula paper that Dr. Garner and I did before, right? So, I think it's almost time up, right? So I want to say from this exercise, even though it's supposed to be a straightforward evaluation, but it's not so straightforward. I think the moral of the story is we need to be able to know our estimators so that we can match the estimator with the target effect of interest, know what we are actually estimating. And even though there's no single method that dominates others, but all is not lost, because in the end, the action space is low resolution. So I will conclude with the advice that's given by Andrew Gelman. How do we decide to believe in the effectiveness of a statistical model or not? He talks about these 1, 2, 3, 4, 7 things, but he said these 7 things are not in the order of importance. So even though mathematical theory, computation stuff is in the front, it doesn't mean really these are the most important part. But you can start off with the coherent mathematical theory and do some toy example for simulation and get some small applications and see if you can improve your performance. And best of all, if you can go out to do cross-validation and external validation, that would be great. And anything that's tested empirically has to be true are obviously useful. And finally, if people want to buy your model, then it's successful, right? So I think I am struggling with 1, 2, 3, maybe 4 of these 7 points here. But I think these are very good advice so that I don't despair in doing empirical research, right? So that's all. Perfect timing, I'll say myself. If you have questions, let's raise them. Thank you.